talking about doing work with my co-author Gunaratnam, who you probably know. Yeah, so this is working, I assume, the microphone. Yeah, okay, perfect. Yeah. So let's start. Yeah, so okay, the first, at least half of the talk was not going to be any of my own results, so it's just to set the stage. So yeah, if we have a random field, yeah, I'll write it a bit nonchalantly here with not really taking into account that it's supposed to be a distribution, but evaluating it at points to lighten the notation a bit. And let's say that, okay, for now, let's say M is a manifold. And B is a submanifold. And okay, let's say that B splits M into, in some sense, into two parts. It should have codimension 1. So an example could be that we have a cylinder and B is a, yeah, it's some splits the cylinder in the middle, or you could have a plane and yeah, B could just be a subplane. And then, okay, this splits your domain into two domains, M1 and M2. Or okay, of course, you can have something of more complicated geometry like this. And okay, you take, you have some sigma algebra, which you can associate to the manifold. So Fm I is generated by the fields in M, and the same for B. And like I said, I'm being a bit nonchalant here. And if F is a functional on S prime of M, only depending on phi in the interior of M1, let's say. And then the field is Markov. If the expectation of f of phi conditioned on the field outside of M is the same as, or yeah, let's write M1 complement, is the same as conditioning on the boundary. Okay. And so, yeah, why is this nice? Well, from this, you can build a quantum field theory in some sense. So Nelson taught us how to build a semigroup from Markov fields. So, a semigroup. Yeah, so if one direction is unbounded, then you can construct a semigroup. And then from the semigroup, you can build a Hamiltonian, and then you can construct a quantum field theory. So the basic example of this is the Gaussian free field. Yeah, so if I have a G of F on M, so this is a Gaussian field. Let's say it has a mass variance m squared to the minus 1, m squared Laschen to the minus 1. Then this can be decomposed in law. So let's call this field phi. Yeah, it's can be decomposed in into two fields, phi m1, phi m2, and three fields, sorry. H phi b, and what are those? So this is, so those are all independent. So this is a G of F on M1 with Dirichlet boundary condition, Mi, and M2 is the same thing. So this means covariance is, so yeah, here of course it depending on if the manifold has boundary or not, I need to tell you what the boundary condition is. But here I have an additional piece of the boundary, so there I put Dirichlet conditions, and let's say here, okay, let's say I start with something which either has no boundary or where I've put Dirichlet conditions on the boundary already existing. So when I add this more piece of boundary, I have to put Dirichlet conditions there. And phi b is just the free field restricted to the plane, restricted to B. Okay. And yeah, so H phi b is the free field. You can obtain its law by restricting this phi m restricted to B. Okay, you have to prove that you can do this, but you can. And H is a harmonic extension. It's the harmonic extension. From B to M. Okay, so yeah, so this, in some form, this is really the Markov property, because you can see that since all of these three are independent, if I look inside my M1, I see this part I don't see because on M1 it's 0. And I see this part. So if I condition on these two, which would be like conditioning on the complement of N1, then I really only see this. So this is, in some sense, the Markov property. Okay, yeah, so far nothing new. And at the level of the path integral, I can write this. So if I look at the action, we can have something like this. Phi, or okay, I'll write it differently. A gradient phi squared. So this I can write as a field which has boundary condition 0, and the field at 0 harmonically extended. So I write phi as like this, and then I see that this is going to give me gradient phi 0 plus 2 gradient h phi b gradient phi 0 plus integral gradient h phi b squared. Yeah, x. So yeah, this is just the free field with boundary condition 0. This I can integrate by parts, and this is going to be 0 because of yeah, boundary conditions and the fact that this is harmonic. And this is some action of my boundary field, which describes its law. So so phi b has a law given by formally, of course. And okay, so the thing is that this depends on the harmonic extension, so it really depends. So here we have something on B, but the law depends on the full structure of M. So even if M is very simple, like it's a cylinder, it will depend on the length of the cylinder. But I can extract, so I can extract from this, I can extract from this a piece which only depends on B and another piece which will be absolute, and this will give me a quadratic form, which will give me a Gaussian. And the rest will be given by some smoothing operator, which I can put into a density. Okay. So, yeah, so much for the free field. Sorry? No, okay, so this is, yeah, so I guess you can do the same. Yeah, so here I did the computation without a mass just to write less, but you can do it with the mass as well. And we're gonna always be in finite volume, so the mass is not so. Okay. So all of this story is closely related to another point of view to view QFT, I guess you could call it, or view Euclidean field theory. Oh no, I erased the wrong thing again. Okay, I'm just gonna erase everything. Which are the Segal axioms. So yeah, I have manifolds. So now my manifolds is going to be in the dimension one less. So those are going to be the B's. And I have cobordisms between them. So, okay, this is like all like very fancy topology words, but it's not so bad. So between, yeah, let's say between B1 and B2. So this just means that I have a manifold B1 and B2. So let's say it's one, they're both a circle, very simple. And then the cobordism could be a cylinder. So it's just something which has about B1 as its boundary and B2. Or okay, I could have some situation like this, where I have some hole. Or I could have a B1 and B2 could of course be different. Then I could have something like this. So to each B, I associate the Hilbert space. And to each M, which I'll just write it like this. So this means it's a cobordism between B1 and B2. And we're going to be in the Euclidean framework. So usually you need to differentiate out ingoing and outgoing, but for us, it's going to be pretty symmetric. So we don't really have to do this. Associate a operator. Yeah, let's call it M of M, which maps H of B1 to H of B2. And of course, this should satisfy some condition. So this satisfies a gluing condition. So if my cobordism is between B1 and B2, or yeah, let's call it M1 and M2, it's between B2 and B3, and then I can compose them. So I can form a cobordism M, which is just M1 glued along B2 with M2. So I just have this. So if I have two pairs of bands here, I glue them together, and then I get something like this. Of course, I have to be careful, but I get like a surface of genus 1. Okay, not able to draw this a second time, but it's this one. And then I would want that the operator I'm associating to M is just the composition of the ones that I'm associating to the respective pieces. Okay, so I just want to say if the M's are cylinders, then this is just the semigroup property. Okay. Yeah, so far, yeah, nothing. Yeah, and you can. Okay, so far this is all pretty abstract and not very. Yeah, maybe not so clear how it's, or yeah, some of you may see how this is connected. So okay, maybe let me, before I erase everything. So the typical situation for us will be that H is L2 of S prime of B. So H associated to B is L2 of S prime of B equipped with some measure. And L is just given by convolution with the kernel. And the kernel will be a quantum field partition function of a quantum field theory with boundary conditions. So I will tell you in a moment how this should look like in a more concrete example. Okay. So in the free field case, this is basically what we just discussed. So there, the mu would be this piece which only depends on B, which gives you a measure. And then the partition function is the partition function of the absolutely continuous piece. Okay. And then you can construct this, and then this operator is going to be the transfer operator for the Gaussian free field, if you know what that means. Okay. Yeah. So next example, 542. So this is still pretty doable. Erase this. Okay. So for 542, so how would you define something like this for 542? Well, so mu, so h of h of B is still given by L2 of on S prime with mu B, where mu B is yeah, it's this piece that I mentioned earlier that I didn't really write down, where yeah, I guess you could call it d phi where this is a sort of differential operator of order 1. And of course, this is formal. This is the Lebesgue measure, but yeah, this is a Gaussian measure. And so let me call this maybe mu bar. And mu is sorry. So the mu without the bar is this, and so this exists and can be computed. And this will, of course, depend on M, but this part doesn't depend on M. Okay. So this is still this guy. And if I want to find the Z, what do I have to do? Well, let's say I start with a partition function of my quantum, of my 542 theory. So let's say I have 0 boundary conditions. Let's, for being very simplistic, say that I have a cylinder. And I have another cut. So let's say this is length O1 and this is length O2, or one and two. And let's say I put 0 boundary conditions on this B, just to lighten the notation a bit. But you can put some boundary condition here if you want. And then this is nothing but exponential of 5,4 dx d mu m. So this is now the regular Gaussian free field on M with 0 boundary conditions. And I can split this because I have a decomposition, as I told you in the beginning. I have a decomposition for my GFF. So I can split this into phi 1 plus h phi b. And this I can, because these are all independent, I can write this as d mu m1, d mu m2, d mu b. Okay. And then I can, of course, I can split this further into d mu b, b bar. And again, this piece I can also factor in and factor into pieces which only depend on M1 and M2. And then I define Z, so what Z1 should be. So this kind of becomes the identity. If I do these integrals here, this just becomes, phi b just it's this piece here. Yes. Sorry, yeah, there's yeah, I forgot this piece, yeah. Yes, thank you. Yeah. Yes. So the Dirichlet to Neumann map, I think, depends on the M. So yeah, this is this one. This is the one, yeah. And then you extract from this only a piece which only depends on the metric of the circle. And the rest is absolutely continuous. Yeah. Okay, so so this is and plus, okay, so this, I don't know, let me call this denote this by A1 times A2 for the parts which depend on M1 and M2 respectively. A1 d mu M1 times M1 A1. Okay, so I need to make sure that this makes sense almost surely with respect to mu b bar. So this part makes sense, this I already told you. And this part, okay, so this is, if I put these back together, I can just get mu b bar. They kind of behave very similarly. So I just need to make sure that I can put actually the boundary condition here. And notice also that I didn't really change the Wick ordering here. So the Wick ordering is still, it's not with respect to the covariance of this. It's still with respect to the covariance of the field on M. And this is over M1. So I need to make sure that all of this is well defined, but if it is, then I can write this formula. Okay, I can approximate some way, I can pass to the limit, and I can prove that this is satisfied. And this formula here exactly tells me that ZM00 is just integral 0. Which is exactly what I wanted. Yeah, so this all works very nicely for 2 dimensions because everything is well defined. Well, in 3 dimensions, things are more complicated. So why is that? Maybe, so in 3 dimensions, it's much harder to actually make sense of this expression. Or yeah, it's impossible actually to make sense of this expression with respect to this Gaussian on the boundary. Because there is a piece which is ill-defined. But you can correct this. But you have to change your measure. You have to change your measure on the boundary. Okay. So in yeah, so in 3 dimensions, so we need additional renormalization. And so yeah, maybe let me tell you, in case you're not familiar with it, some facts about 543. So there, so in 2D, 5-4 Wick ordered is a well-defined random variable. Defined random distribution. So in particular, the average is a well-defined random variable. With respect, almost surely with respect to the free fields. In 3D is not a well-defined random distribution. And in fact, also the cube is not well-defined. And so in particular, so this does not make sense as a density. And we need further renormalization. But even then, we don't get a density. So the prescription is, so we take phi epsilon, some smooth approximation of our field. So, okay, yeah, maybe just to clarify, so the 2D part has been done already by several people. So Pasquale and then Albaverio, Herkron, and Zergalinsky wrote something in this direction in the 80s. And the 3D part is new. Okay, okay, but the part that I'm explaining now is not new, but the gluing part should be new, hopefully. So this is a smooth approximation. So we consider this measure where we subtract some renormalization constant. So we have a quadratic part which we subtract. Sorry, this is a square, of course. And then we have a constant. And this converges if gamma. So this have renormalization constants which are going to go to infinity. Chosen correctly. And okay, let me write this as nu, I guess. Epsilon. And then mu epsilon will go to mu weakly for some mu, which, okay, you don't know because it's a weak limit. But, sorry, nu, of course. Mu and mu are mutually singular. And okay, so this kind of indicates already that there should be some trouble also in the gluing because, yeah, there is some, yeah, so you don't really expect the densities to make sense, almost surely. Okay, so this is mutually singular. So what do you do in 3 dimensions? Or like, what is the issue? We're doing the gluing. So if I want to write my decomposition, then I can do it, but it's not going to make sense. So I decompose the free field as I did before. And then in the end, my problem is to make sense of this. And okay, I'm stuck with the boundary conditions that I chose for the with normalization conditions that I chose for the future. So here I took the infinite limits of gamma and delta to, not write the notation, not bother with the notation too much. And okay, the problem is that this does not make sense, maybe almost surely. So even if I integrate this with respect to mu m1, this does not make sense. Maybe almost surely. So I integrate out this piece. And this piece is, I have to choose fixed according to this measure. And I have to make sense almost surely, but it doesn't work. And why does it not work? Well, because there is a piece here which is very singular, which is going to give me issues, which I need to extract. So because, let me call it star. maybe almost surely, because it contains the action contains this term. So it's the phi b term to the power 4, Wick ordered and then integrated. And okay, why is this problematic? And why does it not make problems in 2 dimensions? Well, in 2 dimensions, so what is this guy? This guy is, you can think of it as a free field restricted to a boundary. So on the boundary, it's the free field, but then I'm harmonically extending it. So as soon as I go a little bit away from the boundary, it's smooth. And in 2D, the divergence is logarithmic. So this is gonna, so this is just, I have to use a little bit of my smoothing and then I can trade the smoothing for boundary blow up essentially. So if I decompose this integral into slices, then, and I measure this in some positive norm, then my positive norm is gonna blow up as I approach the boundary. And in this case, it's gonna be okay. I don't know if it's gonna be, if you can prove that it's gonna be logarithmic, maybe, but it's at worst, it's any polynomial you want, any inverse power you want. So, but here you have an integral over M1, so you can integrate up to 1 over the distance to the boundary. Well, in 3D, you're kind of screwed because this is -1/2 and this is supposed to be -2, so this is way too bad to be integrated. And in fact, you can do the computation and see that this should have infinite variance. So the solution, so this is ill-defined. So the solution to this problem is so that you should redefine your mu b as, or you define mu b, so you define a mu measure on the boundary as this guy. And now, okay, you approximate everything and take weak limits. And then, so you will end up with mu, that the singular with respect to mu b. And then you have to make sure, so now your action, so you have to make sense of this guy where now you have extracted this piece. You have to make sense. Plus. Yeah, the same thing, but now I have just removed this part. Or I've edited, but yeah, I've removed it from here. There's a bracket here. And actually, okay, the second problem that occurs is that here I have subtracted too much in some sense. So So this is taken as, this is going to be an expectation over some powers of the free field integrated. And if I set the covariance, so if I set my free field to 0 on the boundary, this is I'm gonna be subtracting too much in some sense. So there is gonna be, so here it's still okay because the divergence is logarithmic, but here this is gonna give the difference between these two will be a logarithmic infinity. And I actually have to put this here. So I have to make sense of this measure, because I mean, yeah, you expect that you have to renormalize this measure to some extent. So you have to, we have a partition, this measure is, it's singular, but it's not as bad as 543, it turns out. So this has a partition function renormalization, but no mass renormalization. And so you have to extract some renormalization from here, which is superfluous anyway, so you have to extract it. And put it there. And then this will make sense, and this will make sense. And okay, to make sense of this, you have to work. So by work, I mean particular, so yeah, we run our machinery, which some of you may know. So we write this as a stochastic control problem. And then we control this, then this is gonna have a piece which is the regular 543 measure in some sense, and then there's gonna be some parts which come from the interaction of these two. And then you have to control those. And to control those, you will have to construct some stochastic terms for this boundary piece here, or this H phi b. So that you have to do, and you have to do it almost surely with respect to this interacting measure. And you would say, okay, this is a bit annoying because usually you want to do the computations for the Gaussian. So then what you do in practice is that you do the computation for the Gaussian, and then you couple these two together via some more regular term. Like if you'd write to, for example, you can do it with a rational method. You can also do it with stochastic quantization if you want. And yeah, so then once you have done all of this, you can make sense of this maybe almost surely with respect to this measure. You can approximate everything passed to the limit and prove a gluing formula in the limit. Okay, I guess I'm out of time, but yeah, it's 51. Yeah.